All right. Hello, everyone. Welcome back to the lecture. Still setting things up here. And someone is testing the phone. I don't see any responses now. It says 0 responses. It says 4 responses now, but it doesn't show the results. Now that I vote, it is still anonymous. Okay. So did you choose the keep responses anonymous?
Yeah, Professor, I untick the above. That would give me the result just after I submit the vote.
Okay.
And
Yeah,
I tick the other one, which keeps the responses anonymous.
Cool. All right, thank you very much. So let's get it started. Before that, as you can see, my memes are up to date. So I don't know who hacked Facebook yesterday. Huh? Let me know, and your final project will be full mark. So apparently they had a devastating network outage issue that stopped all of their services, including key cards on their campus. And they lost remote, even their employees lost access to servers and routers, and they had to physically go to buildings and restart some routers. All right. Today we're talking about analyzing text. Yeah, it looks like it was a network issue, not a big data issue. In the last few weeks, we talked about core framework features. And we talked about Hadoop, Spark. So we learned a little bit about these frameworks, and we can start programming now. So we have enough information to start thinking algorithm design. And for the rest of this course, we'll talk about algorithm design, so it will be a bit different from what we had before. And our focus will be on analyzing text, more specifically natural language processing. What is that? It's basically the process of trying to understand natural language, right? So it can have different forms, such as spell correction, translation from one language to another one, or these automatic bots that we can chat with, right? So all of these try to understand the language, right? And they do something. And we want to see how big data can contribute basically to this field. So we have already seen a little bit of natural language processing. So we talked about pairs and stripes, and you guys implemented this in your assignment a little bit. But they seem to be pretty trivial. You may not agree with me, but they're really not more than a toy problem. If you really want to analyze a natural language, you need language models, and we're going to talk about them today. When we talk about language models, we are specifically talking about this particular formulation. So we have something like this, which assigns a probability to a sentence. Okay, so these WIs are words in a sentence. For example, Waterloo is a small town, right? So W1 will be Waterloo, W2 is, W3 is A, so on and so forth. And WT is the last word of that sentence. Okay, so these are the words that construct a sentence. And that function P is basically applying or assigning a probability to that sentence. In other words, it means how likely it is that this combination of words in this particular order is a reasonably good sentence in that language. Why should we do something like this? Why should we assign probability? It has many applications. We're going to list a few of them here. Machine translation. So you want to translate something, for example, from Chinese to English, okay? And the way these translators work, they may come up with multiple options for what the translation can be. For example, it can translate it to high winds tonight or large winds tonight. And then we can use this function p to assign a probability to these two alternatives to see which one gets a higher probability, which one gets a higher score. The one with a higher score is probably a better sentence, and in this case, a better translation, right? So that's how we can use that function. Other examples are spell correction. For example, we have two different spelling for great, right? So if you apply the function, we'll see that the left one has a higher score, so it's a better spelling. When in speech recognition, which is another example of natural language processing, we have voice, right? So you talk to your phone. Hey Google, hey Siri, right? And then you say something. So what it tries to do, and I woke up my phone. You say something, and then it tries to understand what you said, right? And again, it has multiple alternatives of what that voice was, and again, it can apply the function to see which one is better. And many other examples of why we should care about assigning a probability to a sentence. So, okay, how can we calculate it, right? Because we want to come up with a number at the end of the day. How is that number calculated? It is calculated using the chain rule. It looks a little bit scary, but it is not. Let me explain. So again, going to assign a probability to a sentence with these words, the first word, second word, and the last word, okay? It says the probability of that sentence is the probability of the first word, right? What are the chances that we see the first word multiplied by the probability or conditional probability that we see the second word given the first word, multiplied by what is the probability of seeing the third word given the first two words, and so on and so forth. And then the last terms of the last term would be what is the probability of the last word WT given pretty much the rest of the sentence up to that word, right? From the first word to T minus 1. I'm going to mute everyone. Please unmute yourself when you want to talk. So that's basically the idea. And if I want to give you an example to make this clear, I want to assign a probability to this sentence, Waterloo is a great city, okay? That would be the probability of the first word, Waterloo, multiplied by probability of second word is, given Waterloo, so on and so forth, right? And then the last one would be probability of city, the last word, given the previous words are Waterloo is a great. Make sense? So this is called the chain rule. So I'm going to stop here for a second and see if there's any questions, because I'm going to talk more about this model, and I want to make sure everybody understands what's going on. Questions? Raise hand or chat. And by the way, nobody turns on the camera anymore. So I have no idea what's going on. If it's okay for you, it would be nice if you turn on your video so that I see your face and see how much I confuse you. All right. So, all right, it looks like it's laggy for some people with camera. So now the question is, I didn't get any questions from you. Let me know if you have any. So the problem with this model or this chain rule is that it is not tractable, right? It becomes very difficult to calculate these terms, right? How can we calculate something like this? And if it's a longer sentence, these terms become even crazier, right? If you have like 10 words in the sentence, it will be the last word, even the last 9 words, and calculating that is not very easy, as we'll see in this lecture. So in order to calculate it, we are going to approximate it because the chain rule is too complex. Okay, so we are going to simplify it. So the idea behind this simplification is that we had these kind of terms, right? That what is the probability of a word given previous words all the way to the first word in the sentence, right? From W1 to WK-1, right? Now we are going to approximate it by the probability of that word only back to a certain word, or a certain number of words. Instead of going all the way back to the first word, right, we want to stop. And that's the idea behind n-grams, okay? So overall, we want to only keep track of n consecutive words, okay? So I don't care if there are more words in this sentence, right? I don't go back all the way to the first word. I will stop at k minus n plus 1, okay? So let me show you some examples. So depending on the value of n, we have different models, right? The simplest one is when n is 1, and this is called Unigram language model. If you plug in 1 to this formula, you realize that this conditional part goes away, right? And this term will be approximated only by the probability of k, because if n is 1, you can see that there's no conditional probability. This part goes away, right? This is the most simple version of this model, okay? So it's simple, easy to do, but as you would expect, when we are going to use it later on, it will not be very accurate. So to give you an example of what it means, I'm going to basically start a game using that pulling technique that we saw. You will see other students' responses, but please think, and because I've already set these up, so you will see the results. So this is the game before I start the poll. I open a book, okay, and I select a random word in that book. Okay, again, I open a book, I randomly select a word. I'm in the first version, which is Unigram. I'm not going to tell you what words appear before that word. Okay, so basically, I'm not giving you any information, right? I want you to guess what that word is. So do your best. So we don't have much information. All I told you is that it's an English book. I didn't say this. It's a book written in English, and I chose a word randomly. What is that word? And I'm launching the poll. So if you don't know what words appear before this word, there's still a trick to find or to do an educated guess, right? It is still pretty random, but it increases our chance of guessing it correctly. It looks like I didn't. Okay, no, I have to go back to the chat, I think. All right. And out of the possibilities that we had, most of you said, if I want to bet, which is really, it's betting, right? Because you don't have much information here. Most of you said it's the, and also we have some responses is, which are correct, right? Can someone explain why you chose those words and not 3, 5, or watch?
It's because those are more common words. Those words tend to appear more than the other words in a sentence.
Exactly, right? We have no information about that sentence, right? All we know is it's a word. So our best bet is to go with the word that is most common, right? So it's a bag with like balls in different colors, right? And I tell you the color green is more common. So if I pick one randomly, if you want to bet what color it is, you would say green because it's the most common color in that bag. And it's the same thing here, right? So probably the will be the best answer because it is the most common word in English and is also one of the common ones, right? So that's good. So that's the idea behind this model, right? So we are going to approximate it just by looking at the probability of that word. That's exactly what you guys did. You said, okay, out of those 5 options you gave me, so the probability of the is the highest. So if I want to guess, I'll go with that. So if this is the chain rule, but the approximated version, right? So all of those conditional probabilities go away, and the sentence will be approximated by the probability of the first word, the probability of second word, so on and so forth. Again, not very accurate, but it's the simplest version. We can do better than this. It makes it a little bit more complex, but more accurate. Now, if n is 2, which is called bigram language model because we use 2 words, right? We want to simplify it now. This term becomes probability of WK given the previous word. Okay, so out of all of the words that appear before that word in that sentence, I'm only going to approximate it by telling you the previous word, right? This is much better than Unigram, right? If you know the previous word, it helps a lot. So let's continue our game. And this time I'm going to tell you what is the previous word, okay? And now you can have a better guess. There you go. Now I tell you that the previous word, when I opened the book and I chose a word, the previous word was apple. So it's apple something. What is that word? All right. So you can see that very soon everything changes. The probability changes, right? Because in this case, so the previous answer was the. If we say apple the, it doesn't really make sense, right? So it's very unlikely now that we know that the previous word is apple. Things that make sense is right. Apple is something, and then or watch like Apple Watch, right? Or tree, apple tree, right? So all of these make sense, and 5 doesn't make sense. So we can see that it becomes all of a sudden it becomes much better, right? It's a much better guess. Now, but it's more complex. Previously, we didn't have the conditional probability. Now we have it. Now we have to keep track of the previous word. So if we want to go back to the chain rule and apply the simplification using bigram language model, it ends up something like this. Ignore the first one. So it becomes the probability of second word given the first word, so on and so forth, the probability of the last word given the previous word. So now the only a little bit strange thing will be there's no previous word for the first word, right? So we come up with this dummy character or word, right, to indicate the start of the sentence. And what it means is that what is the probability that W1 is the first word in that sentence, right? W1 given a start, right? And the rest just makes sense. So W2 given the previous one and last one given the previous one. So that's the idea, right? More complex, right? More complex than the previous version, but probably more accurate. We can just continue this. There's a trigram and some other models, right? N can be any value. So for N3, this becomes something like this. So we approximate it by the two words that appear before that word, okay, like this. And if we want to play the game again, I promise you it's the last time, figure out what the answer is, right? So. There you go. The last one. So now I give you two words before the missing word, and the word is tall. So it's tall apple. Someone says 5. How can you complete the sentence with tall apple 5? I like your answer. So it's most likely a 3, right? Tall apple 3. So we can see as we explore previous words, right, it becomes better, so the model becomes more accurate. So the way we are using this model here is to predict the word, right? Again, it can be for sentence completion, it can be for spell correction, because if you guess what that word is, then you can figure out what is the correct spelling, right? Or is it grammatically correct? So there are so many applications for this. And then if you use this model now, it becomes something like this. Again, these are just dummy characters just to make sure that the model works, right? So again, it means what's the probability of W1 being the first word. And for any word, we basically approximate the chain rule by saying probability of that word given the two previous words in trigram, right? So that's the idea. How can we actually build these models? Okay, we got an idea of how they work. How can we build them? One way to do this is to use maximum likelihood estimates. Easy. You have been doing this in your mind already, just fancy names. So, for example, for Unigram, the way we basically train a model is that we have some training text, okay? And on that training text, we are trying to come up with these probabilities, for example, in Unigram, right? How do we calculate probability? Easy. It's you count a word and you divide it by the number of words you have, right? That's the probability of saying a particular word. And that's how you thought the is probably the common one because the appears most. So its count is the highest in a given text, right? So when you divide it by the number of words in the document, it will be the highest. So how if we do not have enough previous words as conditions? Do you mean when it's the beginning of the sentence that we don't have enough words? Is that what you're asking? Or the sentence is too short, maybe? Let me know. I'll go back to your question in a second. So that's for Unigram, because all we needed was the individual probability of words, right? No conditional probability. So that was it. So we could easily calculate it. For bigram, it becomes a little bit more complex, but it's pretty easy. So in bigram, we need the probability of like joint probability, right? So what's the probability that we see two words back to back, like Chinese food, right? Again, what's the probability? You count how many times you see these pairs of words in the text, right? And then you divide it here. Sorry, my notation is a little bit confusing. N is different here, right? So here, N is the number of pairs of words. Here, it was the number of words. Here's the number of pairs of words, okay, that you have in the training document. And then using this, I can calculate the probability of Wj given the previous word, okay? And that would be the probability, the joint probability, right? What's the probability that I see these two words together, like Chinese food, and then divided by the probability of the previous word on its own, right? Like Chinese. And if in the best case, every time Chinese appear, food appears as well, so it will be 1, right? If otherwise, which is the case typically, this will be a lower probability divided by a higher probability. It will be something between 0 and 1. And then we are approximating this, and it's not an exact value. We are just approximating it by, so we're saying this probability is basically count, or the number of times these two words appear, divided by n, right? And then the probability of single word is basically we are approximating it by sum of number of times this word appears with other words. Okay, we used this notation before. So that would be the count of that word. Okay, so remember that we are doing some approximation here. This is not exact, but we can figure out that the probability of a word given the previous word is the number of times those two words appear together divided by the number of times the previous word appears on its own. Okay, and the beauty of this is that we know how to implement it in MapReduce, right? Because you know how to calculate word count, right? And also you can do count of pairs of words, right? So it's easy. Now, in reality and in the state of art models, they typically use 5 grams, okay? So they look at the last 4 words. Okay. Kian, I did not get a follow-up clarification on your question. Let me know, because I wasn't sure what you know, but we don't have enough previous words. I have an example that may clarify your question, so you can wait to see. Yes. Yes, this is, you have a question, is, are these two things the same? Yes, it is the same. Because this part is coming from just conditional probability, right? Nothing special. It's a probability of joint divided by the probability of the condition. All right, so nice. So we can do this in MapReduce, and we are not going to bother showing the code because we know how it works. So that's basically how these language models are trained. And I'm going to show you an example of training the model and then using that model. All right. And in this example, we are going to use bigrams, okay? So I got a question, is n for the joint probability and the individual probability different? Yes, they're different, right? Individual one is the number of words, and for pairs, it's number of pairs. So let me show you an example to see how it works. So the model is going to be bigram, so we only look at the previous word, right? So this is my training corpus, okay? It's a little bit stupid because it has only 3 lines, but this is how much I can fit in one slide. We add these special dummy words just for the model to work. So we have these like start of the sentence and end of sentence dummy words, okay? So that the mathematics work. This is how we train, okay? So we are going to basically find from this training data, we want to come up with all of these conditional probabilities that we have in bigram, right? So let's start with something straightforward, such as this. What is the probability of am given I? So going back to that model, it is basically the probability, or we said the number of times that these two words appear together, I am, right, divided by the number of times that this word I appears in the text on its own. Okay, so let's first count how many times we have I am. 1, 2, and nothing here, right? So it's 2 divided by how many times we see I? 1, 2, 3. So the probability of m given I is 2/3 or 0.67. Okay, makes sense? And then how about this one with the crazy dummy word? So this is basically saying what's the probability that I is the first word in a sentence, right? Because it says what's the probability that we see I after the start token, right? So now we have to see how many times we have this combination, start I. Let's count that, start I. So it's 1, and that's it. Oh, sorry, 2, right? So that's the number of times that they appear together. So 2 divided by the number of times this token appears on its own. So 1, 2, 3, right? So again, 2/3, same probability. How about do I, for example? How many times we have I do? Once. So it will be 1 divided by how many times we have I? It's 3 times. So it's 0.33. Makes sense? So using the training corpus, which in reality is gigabytes of data or even terabytes of data, we train the model, and that means we find these conditional probabilities that the bigram model requires. So we have a question about the ordering. So here, actually we care about ordering. The reason is this conditional probability is all about ordering, right? Because it says, what's the probability of seeing M given I? So given that the previous word is I, what is the probability that this word is M, right? So it's very important that when we search, we actually care about I am and not am I, because that would be a different thing. Make sense? So now we got a trained model. Okay, so we got a question. Why is probability of n given Sam is half? This one, right? So what is the probability, right, that we see this end token given that the previous word is Sam? So in order to calculate this, I have to see how many times I see Sam and then this end character, right? So basically how many times Sam is the last word in that sentence. So once, that's it, right? So it will be 1 over how many times we see Sam? 1, 2. So it's half. Out of the 2 times that we had Sam, in one case it was the last word. So now that we have this, and okay, I have a note that we don't ever cross sentence boundaries when we say which word is the next, like behind what word. The context is a sentence, so we don't go to the next sentence. So now that I just copy that data that we calculated here, and now I'm going to use this model to assign probabilities to new sentences that I haven't seen, okay? For example, there's a sentence, I like ham, okay? Let's assign a probability to it given the model that we trained. So if you write it using the chain rule, obviously the approximated version, because we are using bigram, right? It will be something like this. What's the probability that I is the first word? What's the probability of like given I? What's the probability of ham given like? And what's the probability that ham is the last word? Make sense? We go back to our training set. For example, here, I given start, we have it. It's 0.67, right? So we find it. And then like I, we check, right? And soon you'll realize that, well, we do not have some of these terms. I believe we didn't have like given I, or we didn't have ham given like. So because we didn't see these combinations in our training corpus, the probability is 0 because we didn't see it at all. So when we are trying to calculate the probability, it will be 0. Why is this bad? And let me tell you something. You may say, wait a second, your example was stupid. It had only 3 lines. That's why you didn't see many combinations. But if you train it on a gigabyte of data, then we see combinations. Correct that this will happen less likely, but it still happens very frequently, because it's very likely that we don't see a combination of words, especially when we go to higher values of n, right? So a word given like last 4 words, then it's very likely that I didn't see this combination of words at all, even if I train on gigabytes of data. But why is this bad? What's the problem here? I assign 0 to it. What's the problem? So we can also rely on part of a speech instead. I'm not sure if I am following. Can you clarify? So yes, I'm getting some answers that all make sense. The issue is that, as I said, it's likely that you don't see a combination of words. The problem is that as soon as one of these terms becomes 0, the whole thing becomes 0, right? And this only has 3 words. So if it has like 10 words, there will be many, many more terms, right? And again, one of them 0, the whole thing becomes 0. But this is an okay sentence in English, right? The problem is that we're giving it 0. The problem is, the root cause of the problem is that even if you train it on a big data set, it's possible that we miss some of the combinations and that the whole thing becomes 0, right? The issue is the sparsity, right? That these pairs of words are sparse. So there's a chance that we don't see some of these combinations in the training corpus. So if you have not seen a combination, assume some default probability. That would be one of the solutions. So let's go and talk about the solution. How can we fix this, right? Because of the sparsity, you'll see that there are combinations that have 0 probability and they just crash the whole thing, right? Because we are multiplying. So how can we fix this problem? By not a smoothie, but a smoothing, okay? About that. So zeros are bad for a statistical estimator because we use maximum likelihood estimate and we multiply everything and the whole thing becomes 0. So we have to make this distribution smoother, right? Because right now some combinations have non-zero probabilities and many combinations have 0 probability, right? So the probability distribution is not smooth, right? There are different techniques for solving the problem, but all of them kind of follow what we call Robin Hood philosophy, that we take from the rich and we give to the poor. Okay, so I'm getting like Albert, for example, suggested this, or Man suggested something like this, that we are going to change the probabilities a little bit, okay, to get rid of the zeros, to make the distribution smooth. And the idea is the many different techniques. So we have Laplace, good Turing, and many other techniques as well, okay. And I'm going to explain one of them here, which is actually what's suggested in the chat. So Laplace smoothing, again, fancy words for simple ideas. Whenever it's a fancy name, it's typically the name of the person, and that's the case. Laplace is a scientist. So the model is very simple, and the idea is we're going to add 1 to all terms. Okay, so as the suggestions said, we assume that we have seen everything once, okay, even before processing the training text. We assume we have seen everything once. The nice thing about this is that later on, when we are using the model, it doesn't produce any zero. It will be a very small number, right? Very close to zero, because if we don't see that combination, it will be 1 divided by the number of pairs, for example. It will be a small number, but it is not zero, right? So when we multiply it, it will become a small number, but it's not zero, which is what we want. So we basically add 1 to everybody. So that's the idea. But we need to revise our formulation because these are probabilities, right? Which means that they should add up to 1, right? That's the rule of probability and distributions. Right now, the suggestion is that, for example, when we have unigrams, we can add 1 to everything. So we say that, oh, I've seen every word once, okay? But the issue is that because you are adding those plus 1s to every word, now if you add up all of the probabilities across all of the words, you will see that it's more than 1. So this breaks the rules of probability distributions. In order to fix it, we should modify the denominator as well, so that at the end, when we take the sigma over all of the words, it adds up to 1. So if you think about this, the assumption was that we add 1 to every word, right? So even those that are not in the text, and that was the whole point, right? So for every word in the vocabulary, you are going to add 1. You're saying that I've seen every word in English, regardless of what text I'm processing, okay? So the denominator, n, what was n? N was the number of words in that document. Now we should add the number of words in the vocabulary, anything that may not be even in the text, right? So this is the size of the vocabulary. And this fixes the probability distribution because we have added 1 to every word. And now we are adding 1 to the denominator for every word, which will be v, the size of vocabulary, okay? Bigrams. So again, we assume that we have seen every pairs of words, okay? And again, here we care about the order. It's a little bit different from some stuff we had in the assignment, right? So we are basically adding 1 to every pair. So we are saying that every pair of word in English has been seen even before processing the text. So to fix that, we have to add vocabulary squared. Makes sense? Because how many pairs do we have in English? If the size of the language or the number of words in the language is v, the number of pairs is v squared, right? And that's how many ones I've added. So I should add v squared to the denominator to fix it so that when I add them up, they add up to 1. Make sense? There are issues, right? It's a simple, and I noticed that my camera is blurry. Okay, so it's a simple technique, very simple technique, right? So it's nice in that sense, but its performance is not great. That's why there are many other techniques in addition to this, and there are some shortcomings, such as what happens if we don't know v, or we cannot estimate it very accurately. What happens? Then we should use more complex techniques. Okay, so I just wanted to present one example to give you an idea of how these smoothing techniques work. Okay, so we modify the probabilities to get rid of zeros. That's the idea. But how we do it, there are many different techniques. So that's the end of this part. I'm going to talk about another topic now. Is there any question? All right. Let's start a new topic. Again, in analyzing text. And that topic is searching. Okay, search is an interesting. Okay, there's a question. V is the number of words in English. N is the number of words in the document. Okay. So You can do these simple changes, and then we can develop in MapReduce, meaning that we can basically process or train models on large data sets easily. So that's nice. Now the next topic is search. Search is interesting because searching for something in a collection of many documents is difficult. In the context of web search, again, very difficult. We are dealing with billions of web pages, and searching for something in such large collection is not easy, right? This is basically what Google does, right? It retrieves things in a fraction of a second for you, but the possibilities are like numerous, right? There are billions of documents out there, but it can quickly retrieve the results for you. It's a very interesting big data problem. So when we talk about search, what do we mean? So this is the high-level architecture of it. So we have a searcher, right? So you, for example, trying to search for something, and then we have an author like Shakespeare, right? That wrote some text. And the idea is that you have some concepts in your mind. You want to search for something, okay? And you come up with some query terms. These are the words you enter in the Google search box, right? Query terms, things that you want to search for, right? The author also had some concepts in his or her mind, right? And they have the document terms, the words that that author put in the document, right? And now we want to basically find the documents that match those query terms, right? But this turns out to be actually a very difficult problem. Example, you search for tragic love story. Well, Shakespeare does not use such cheap words, right? He will use faithful star-crossed romance. Although both of you are thinking about the same thing, or the concepts are the same, but the words are different. So it's very complex, and there are many other complexities in language, right? So we have the structure of the language. So basically, if you want to develop a search engine, does it mean that that search engine should understand every web page? And what does that even mean, right? The computer cannot understand what's on that page, right? So how can we find the stuffs for people? How does Google work? This is the abstract architecture for IR, or information retrieval. So we have a query, right? This is what you search. There are documents like web pages on the internet, and there are some hits. So this is the search result page of Google, for example. The documents must be represented somehow, right? Because it's computers, right? We have to somehow represent the documents. They don't understand documents, right? We want to create an index that we can use later to look up stuffs. So we have the query, we want to represent that query somehow, and then we want a comparison function to say, hey, yes, for this query, this page makes sense. We want to use that index to find suitable pages. I'm going to talk more about this architecture. The right part is offline, so Google can process all of the web pages, and it can take its time. Even a week is fine, right? A day is fine. But the left part is the online part. This is when you enter something and you want to search for something. You want results quickly, right? You don't want to wait a day, right? So the left part must be quick. And there are some other technologies like web crawling, for example, for web search. Okay, we have to go and find web pages and things like that. We don't talk about those things here. We assume that we have the document somehow. And we're going to talk about the indexing process, okay? Well, the issue is that computers do not understand anything, right? AI, as we'll talk about, is a little bit misleading. So computers cannot understand pages, so we cannot expect them to go on a page and understand, okay, this is what's on this page. So if somebody searches for this thing, I'm going to match it. No, it's not going to work. We need an idea. We need a way to represent documents in a way that we can match it with the queries, right? And there is this simple idea called bag of words. This technique is awesome. It's so simple, but yet so effective. It says, I am going to represent a document by just the words that appear in that document. So I just tell you, okay, the way we are going to represent or know what's in that document is that I tell you the word count basically of the document, that these are the words that appear in the document. This is how many times they appear in the document. That's it. You throw away grammar, you throw away structure, everything. I just tell you, these are the words that you have in this document. It's a very aggressive simplification, right? We're throwing away a ton of data. Can we actually search using this simple representation? It turns out, yes, it works actually very nicely. Is this what is used by people who do search engine optimization? I'll talk about it a little bit later. So search engine optimization is basically what words, there are other techniques as well, what words you put on a page so that when somebody searches for something, your page becomes one of the top ranked pages on Google. That's search engine optimization. And the assumptions here, a ton of assumptions, basically. Some of them are term occurrence is independent, document relevance is independent. You will see later on when we talk about the models. And even things like words are well defined. What the hell does that mean? Words are well defined. Words are well defined, aren't they? Well, shoot. No. The search engine, right, needs to work with different languages, right? And for example, for me, and I believe this is Mandarin, for me, the definition of word is not clear. I don't know what is the first word. I just see a bunch of characters, right? So how does a computer can figure this out? Make sense? So that's tricky, right? It's difficult, right? For now, we assume that everything is well defined. Here, again, not very clear. Maybe there are space, I'm not sure. This, I believe, is Russian, right? And for legal reasons, I do not know that because I may or may not be on some torrent forums, right? Because we do not download anything illegal, right? But it looks Russian to me. All right. So so that's the idea. For now, we assume that words are well defined and a ton of other assumptions. Let's talk about this bag of words idea. I have an article here. This can be a web page. I want to apply the idea of bag of words. And here you will see how beautiful this idea is. So the bag of word idea says, I don't care what you have in that document, the structure of the sentences, grammar, just throw all of that away. Just keep what words we have in that document and how many times it appears in the document. That's it. But you will say, but this is too much simplification, right? We lose the meaning and all of that, right? How can we figure this out? Wait a second. Let's look at the first most frequent words in this document. McDonald's, fat, fries. Stop here. I have a pretty good idea of what this article is about, right? This is the beauty of bag of words. So despite being a crazy simplification, you can still figure out what this document is about. And now you can use this representation to match these words with the queries, right, that users enter, right? And we are going to talk about it. It's much more complex than this. Exactly, right? Those 3 words are enough to figure out what this is about. A good idea what this is about. And you can also look at other words. So that's the idea. We convert documents into bag of words, and then we use the bag of words representation to create what's called inverted index that we use for search. We do case folding, tokenization, stop word removal, and stemming, things like that, but we get rid of syntax, semantic, word knowledge, and some other stuff in natural languages. It's amazing, right? How much we simplify. Now, so technically, the search problem became the counting problem, right? That we are pretty good at. So now it boils down to, okay, we have these documents, and in order to create this index that I'm going to talk about next, just by doing a word count, right? We want to know what words appear in what documents. So I have, like always, I have crazy examples. I have 4 documents that they have only a few words in them. Okay, sorry about that. So I have 4 documents, some word, and then here what I want to create, simple. So I want to know in each document what words appear, right? For example, blue. The word blue appears only in document 2. So in this matrix that I have, I put 1 here to indicate that document 2 includes word blue, right? Or the word fish appears in document 1 and document 2. Okay, so on and so forth. You can complete this matrix, right? That tells you which word is in what document, right? So what goes in each cell? It depends. In the simplest version, Boolean, right? So does the word appear in that document or not? It will be the Boolean version. Or you can put the count there, right? How many times it appears in the document, right? Or some other information like positions. Where does it appear in the text, right? Or like things like, is it in the title of the article? Is it in the body, right? So, or other information. So you can put anything you want. So it just makes it more complex and probably more accurate if it's a reasonable thing, but it makes it heavier, right? So we are going to talk about this part, indexing, right? And then later on, mostly next section, I'll talk about retrieval part. So this is indexing, okay? Indexing is building this structure. Retrieval is manipulating this structure to find out which documents are suitable for a query. Instead of having a matrix, and because as you guess, it will be a very sparse matrix, right? Because a word may not appear in 99% of the documents. So it will be like zeros for like billions of columns and only 1 in some columns, right? So it will be a very, very sparse matrix. So it will be a bad idea to store it that way. So we use linked lists, okay? So for every term or word, we have a linked list. It's the same data, right? It says fish appears in document 1 and 2. These things, the purple, pink things, boxes, are called posting lists. Okay, so these are the postings for this term. Okay, so terminology. So it's technically a large sorting problem, and as I will tell you later on, these postings must be in sorted order. All right, so the document IDs must be sorted. I'll tell you why later. So it's a big sorting problem, and typically terms fit in memory, right? Because how many words do we have in a language? So probably words or terms, right, fit in memory, but postings usually do not. We'll talk about how we can do this on a single machine and how it can be done with MapReduce. before we start, okay, I want to wrap up this lecture, but talking a little bit about a characterization of this problem. Always for any data science project, always try to characterize your data set. Try to understand what type of data you're dealing with, how big the data is, right? So here, my data looks like this. We agreed to do indexing this way. Two main questions. How many of these terms do you have, right? For example, if it's English, and if you're processing like 10,000 documents, how many words do you expect to get? We have to understand this, right? And also, like how does these postings look like? How many do we have? Like, is it kind of uniform? Is it not uniform, meaning that some words appear more, some words less? How does it exactly look like? This is what we mean by characterization of the problem, to understand the behavior of that data structure. So we're interested to know the size of vocabulary and size of postings, basically how many terms we may see, and then how big these postings will get, right? So this is how we model the vocabulary size for a given number of documents. So M is the vocabulary size. So how many terms do we see, right? How many rows do we have in that data structure? For a given number of documents. So T is the number of documents we are processing, okay? And K and B are some constants. K typically between 30 and 100, and B is between 0.4 and 0.6. All right, so it's a simple model, but it gives you an idea of how many words we have. So this is called Heap's law. Okay, it's a linear in log space. I'll show you a plot. Okay, so your y, if your x and y axis are in log scale, it will be a line. The crazy thing is that vocabulary size grows unbounded. Because what prevents M to grow here? So if you add more documents, you should expect more words. That is crazy. It should look like something like this. The dashed line is what we get from the formula if K and B have these values, okay? And then the x-axis, which is the number of documents, T is in log scale, and the number of vocabulary is also in log scale. And the solid line is actually the actual values from a particular collection. As you can see, here we have a little bit of discrepancy, but overall, it fits the model pretty nicely, right? So that's about how many lines we should expect, right? So it will grow unbounded. We have to remember. It's not like, yeah, we'll have like 10,000 words in English or whatever, and that will be it. No, it's wrong. It will grow unbounded as we increase the number of documents. It will slow down, right? So if you process 1,000 documents, you find these new words, and then you process the second 1,000 documents, the number of new words that you discover is less, but you keep discovering new words. And then this is the last thing we want to mention. This lecture is how the posting size look like. It follows a different law called Zipf's law. And I have a very nice video. So let's watch this video and wrap up this lecture. So there you go. And I think I should enable this so that you can hear the voice. The video is 20 minutes, but we're only going to watch the beginning of it. And if you're interested, you can watch the rest on your own. If you search for Zipf's law, you can find it. Let me know if you can hear and see the video.
Hey, Vsauce, Michael here. About 6% of everything you say and read and write is the. The is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are The of and to, a in is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on, all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line, a power law. This phenomenon is called Zipf's law. And it doesn't only apply to English. It also applies to other languages like, well, all of them. Even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this. According to wordcount.org, which ranks words as found in the British National Corpus, sauce is the 5,555th most common English word. Now, here is a list of how many times every word on Wikipedia and in the entire Gutenberg corpus of tens of thousands of public domain books shows up. The most used word, the, shows up about 181 million times. Knowing these two things, we can estimate that the word sauce should appear about 30,000 times on Wikipedia and Gutenberg combined. And it pretty much does. What gives? The world is chaotic. Things are distributed in myriads of ways, not just power laws, and language is personal, intentional, idiosyncratic. What about the world and ourselves could cause such complex activities and behaviors to follow such a basic rule? We literally don't know. More than a century of research has yet to close the case. Moreover, Zipf's law doesn't just mysteriously describe word use. It's also found in city populations, solar flare intensities, protein sequences and immune receptors, the amount of traffic websites get, earthquake magnitudes, the number of times academic papers are cited, last names, the firing patterns of neural networks, ingredients used in cookbooks, the number of phone calls people receive, the diameter of moon craters, the number of people that die in wars, the popularity of opening chess moves, even the rate at which we forget. There are plenty of theories about why language is ziffy, but no firm conclusions. And this video doesn't contain a definite explanation either. Sorry, I know that's a bummer since we appear to like knowing more than mystery. But that said, we also ask more than we answer. So let's dive into Zipf's ramifications.
All right. Sorry, the video was a little bit out of sync with audio because it captures my screen. I think it's tolerable, not for gamers. Sorry about that. So that's the idea, and that's how we basically model the words, right? So how many times do you expect a word to appear in a document, or in how many documents you expect it to appear? It follows a Zipf's distribution. So some words appear in almost all documents, while many words appear only in some of the documents, right? So that's how the posting lists. So the posting lists are very skewed, right? Because some terms have very large postings list, but some terms have a small postings list, right? We are going to talk about this more and going to talk about the MapReduce implementation of indexing next time. I'm going to stop the video here and I will be around for a few more minutes.